quite a bit of what we've been learning so far has been building up to the concept of homeostasis. And while we haven't sort of formally defined it, perhaps as yet, we can do so now. Homeostasis is the following, and you're doing it right now as a biological organism, and this is occurring continuously. It is the maintenance of a constant internal environment to enable optimal conditions to function. So we've really got two specific parts here. We've got constant internal environment. Think about body temperature, for example. It's a great example of this, how the human body is capable of maintaining body. We'll do a bit of this in detail, but maintaining at 37 plus or minus 1 degree Celsius, despite what's going on in the external or internal environment. And in order to do that, or because of that, optimal functions, for example, enzyme activity, enzyme function, non-denaturing of enzymes can take place because of things like temperature. Now, this is achieved through what we would call negative feedback loops. Negative feedback loops. And that may or may not be obvious to you at this point, but I'm just going to give you almost like a blank impression of what we mean by a negative feedback loop. And don't worry, I'm going to sort of get this to be sort of clearer to you with some applications. But what we're talking about here is some sort of notion of optimum level. Now, I'm going to do this without any particular values at the moment, but we've got some kind of optimum level. Think about things like temperature. Think about things like thyroxine levels or other hormone levels. Think about things like blood glucose, blood pH. We've got an optimal level of those in each cases. Now, for example, let's imagine that the level, for some reason, increases. You know, body temperature could go up because you start exercising, for example. Let's imagine that we've got something like that increase being detected by receptors. Those receptors could be thermoreceptors that inform the hypothalamus, and because of the increase in, let's say, temperature, we get some kind of response, and that response could be, for example, sweating. So we get some kind of response, and therefore we return to the optimum level, 37 degrees plus or minus 1 degree, say. Now, if, for example, we get a decrease, the external environment is cold, let's say, what will happen there is that this will be picked up by receptors, thermoreceptors in the blood, for example, and those receptors will stimulate some kind of response. And if it was temperature, this could mean that we're feeling cold and we would experience something like shivering, or the rising of the increased tone of the erector pili muscles, for example. This would return us potentially to our optimal level. So that is what we mean by negative feedback loops. Now, what I'm going to do is I'm going to quickly select the right layer, and what I'm going to do is I'm going to select my little sort of model again. I'm going to hit the old Command C. Where are you? Command C, Command V. And what we're going to do here, I'm now going to kind of drag this down, and we're going to start making applications with this. So what we've got our model again here. Now, I want you to notice the nuance of what we're going to do here, folks. So what we're going to do here, first of all, is we're going to talk about blood pH. Now, blood pH is how acidic or alkaline, or indeed neutral, the blood is. Now, what the blood should be is in the range of 7.35 pH to 7.45. So, of course, anything outside of that is problematic because, for example, let's say that we had a decrease in blood pH, more acidic conditions, that could denature enzymes and have other impacts. So let's just say that here we get, let's just say that we start to exercise. Okay, so you start a training run, you jump on a treadmill, you jump on an exercise bike, you go for a walk, whatever. So exercise starts. What would happen to blood pH in the context of exercise? Well, of course, what would happen in this case is we would get some kind of decrease in blood pH, okay? So it would become more acidic. If we said blood acidity, this, of course, would say increase, right? Because it'd be more acidic, but, of course, lower pH, meaning more acidic in this case. So we get a decrease. This is picked up by receptors. Remember our receptors. So we have chemoreceptors, not enough space, chemoreceptors that are in the aorta and also in the brain, and those chemoreceptors detect a decrease in pH or an increase in acidity levels, and they stimulate some kind of response. Now, what response would we expect here? Well, we would have an up arrow, an increase in heart rate, an increase in tidal volume. So we are effectively going to pump more blood more frequently, and that, of course, is going to help to reduce and remove the factors that are causing a lower pH, lactic acid, carbon dioxide, and then we're going to return back to our stable levels, okay? But let's take another example. What happens if that was what happens if we go here? I was meant to be green, by the way. What happens here? We stop exercise, we go into recovery, we go into a warm down, whatever, recovery. So what's going to happen? We're not exercising anymore, perhaps, or not so much. Well, now blood pH is going to increase from where it was. Why? Because we are not producing as much lactic acid, not producing enough as much carbon dioxide. We're going back towards kind of resting levels. So what would happen here? Well, the chemoreceptors now, because the blood pH would now be rising again, I haven't got space for that, but the chemoreceptors now, they're going to detect an increasing pH level, and they're going to produce, or they're going to stimulate a response. And this time, in this case, the cardiac control center is going to decrease heart rate, and we're also going to get a decrease in tidal volume from the breathing muscles contracting less forcefully. And therefore, we're going to help to return our blood back to its neutral pH. So exercise encourages the body out of homeostasis. But our negative feedback loops, and you might notice here, involving numerous different organ systems, these will, working together, these will bring that homeostatic condition back to optional levels. In this case, 7.35 to 7.45 blood pH. But let's do something else. Let me just copy that again. So I'll leave all the words behind, but I'll copy this. Command C, Command V. There you go. And what we'll do now is we'll move this one down, and we'll... Oops, that was not what I meant to do. I meant to do... Let me do that again. Sorry, folks. That was meant... I see what I did wrong. So let me do this. I'm going to... Sorry, folks. Bear with me a second. I don't want that anymore. So let me get rid of that. So now what I'm going to do is I'm now going to do it correctly. I'm going to copy this. Please work. I've now pasted that. And hopefully... Oh, brilliant. It hasn't worked for me. Aren't I doing well? What a wally. So what I'm going to do here, folks, I'm just going to kind of draw this in hand. Okay, so just bear with me while I do this, because what we're going to do now is we're going to look at body temperature. So I'll do this in sort of blue. I'll do that in sort of blue. So here's my body temp. Okay, I'm going to choose a different blue. But we should know that body temp should be in the region of 37 degrees Celsius plus or minus 1 degree Celsius. So that is the optimum condition. Now, what happens here if we start to exercise, okay? Or it's hot outside, so we've now gone to exercise. So, of course, we are releasing heat. Those exothermic reactions are taking place. And what's going to happen here is we're going to get an increase in body temperature, an increase in blood temperature. What's going to happen? Well, this is going to be detected by our thermoreceptors. We've looked at these before, depending on which tutorials you've done. It's going to be detected by thermoreceptors in the skin and in the blood. And those thermoreceptors are going to cause a response. And that response is going to be controlled by the hypothalamus, which of course is responsible for blood temperature, for body temperature. And what we're going to get is we're going to get vasodilation of blood vessels to the skin. Vasodilation to blood vessels to the skin. In other words, more blood's going to pass by the skin. And we're going to get vasodilation... vasoconstriction. Sorry, folks. That copy and paste through me. Vasoconstriction to the core, to the inner parts of the body. So the blood is going to be pushed past the skin to cool it down, and therefore we're going to return to our optimal conditions, even though we are exercising. It helps us to cool. Now, what if we now go into recovery, or we go into cold conditions, or we fall into cold water or something like that? Well, what we're going to get here, and let me just change colours to something. We're going to get a decrease. We're going to get a decrease in body temperature. Again, that is going to be detected by our thermoreceptors, skin and in the blood, thermoreceptors, and they are going to produce a response. Now, this time, we could kind of get the switching back of this process. We could get vasoconstriction to the skin and vasodilation to the core of the body. We'd get that as well. But we'd also expect to find things like shivering. And remember that shivering is an efferent autonomic nervous system response. It actually does it itself. We might see the adrenal gland firing and releasing some adrenaline that will increase the body's metabolic rate, and that might help us to return this time back up in temperature to stable body temperature. Now, before we leave thermoregulation behind, temperature regulation, I just want to make a couple of points. Thermoregulation is affected by something. So that model I just showed you, that is going to be affected, regulation, it's going to be affected by the following. It's affected by these things. First of all, your training status, your level of fitness, for example, will increase. If you're particularly fit, it will help you to thermoregulate more efficiently. We're going to do more of this when we come to impact of environment. Also, one's body composition is going to affect a person's thermoregulation. Now, you can look at that in different ways, actually. You could say, okay, people who have more subcutaneous fat, more fat under the skin, we might say, okay, more of an insulating layer helps to keep warm, for example. But of course, the other thing is someone that exercises and perhaps heavier than they could be, they're going to experience greater work, and therefore their tendency to increase body heat and is going to be greater, and their ability to regulate that's going to be more difficult. The environment, of course, affects thermoregulation. Think about something like humidity. We're going to come back to that. It's actually hard to cool off in humid conditions, for example. We might also get sex differences, but when I talk about sex differences here, we're talking about males and females. We generally find that women have more of an insulation layer than men on the whole, and it could also be to do with hormonal cycles. So we've talked about this before in previous tutorials if you've taken them. So we could be talking about the stage of the menstrual cycle and the presence or not of progesterone, for example, so which increases body temperature. So those factors influence thermoregulation. Now, last thing from me in this particular tutorial, folks, I just want to address with you the regulation of blood glucose, because that's one of the ones I could have done here. Okay, I could have done a negative feedback loop for blood glucose, very similar to what we've done already, and I'm sure it's fairly common sense for you. But there's a couple of factors that influence this. I want you to be aware of the following. Exercise limits insulin production. Now remember, insulin limits insulin production. Now remember, insulin is a product production. It's a product of the pancreas, which is released in the bloodstream and helps glucose to enter cells. It also helps glucose to be stored more efficiently in the liver. So of course what happens is if we exercise, we are utilizing our blood glucose, therefore the requirement of insulin production decreases. So exercise is good for limiting insulin production. So exercise positive, thank you. Secondly, we also find that exercise facilitates, think just helps is a better word, a different way of saying that, facilitates glucose uptake. So remember, if we are exercising, we are likely to be doing that was meant to say uptake. I think I've written upated. Let me write it down properly. Uptake. When we are exercising, more glucose is being utilized for both aerobic and anaerobic respiration, and therefore our uptake of glucose is higher, and that is one of the reasons why insulin production is less necessary. Thanks.